Perfect. Well, welcome everyone. I appreciate you attending. My name is Matt Ellis. I'm currently an assistant professor here at UC Davis within the chemical engineering department. So yeah, I'll be talking about model predictive control for energy systems. This is a key near and dear topic for me. I spent the last 8 years, I guess, 8+ years in the area of model predictive control. So excited to talk to you all about it. Okay, so model predictive control, as most control, to describe it rigorously, it requires some really in-depth mathematics, and it's more depth than I want to talk about and too dense for a 20-minute talk. So I'm going to just try to touch on the key points of model predictive control. What is it? Hopefully this will motivate why we want to use it in energy systems. Then talk about some of my my recent work in the area and sort of conclude after that. So just want to touch a little bit about what is model predictive control. So it's a feedback control technology. It's really useful because it accounts for performance considerations over a prediction horizon. So this concept of prediction horizon will become important as we talk about energy systems. It also addresses constraints all within a systematic framework. So the key parts to a model predictive controller is really it encompasses two parts, finite control or finite horizon optimal control problem and receding horizon implementation. Again, don't want to necessarily get into the deep mathematics here, but I do want to touch upon it so anybody can sort of understand what is MPC. So as I said, I'm a chemical engineer by training, but as you'll see in my talk, most of my focus is in the area of buildings, which is not typically a chemical engineering subject. And the reason why is mainly how model predictive control has evolved over time. So model predictive control, MPC, is evolved out of the chemical process industries. So most of the early work was even dating back to the 60s. And it's been widely adopted in the chemical process industries. And it's been so successful at reducing operating costs, increasing throughputs, that it's fathomable to say that MPC is a billion-dollar technology given its savings and increased profit potential just within the chemical process industries. So it's been adopted now in other industries, including within the energy sector. But more specifically, within the last 10 or so years, there's been numerous theoretical advances in MPC, and more specifically, a more general format of MPC called economic MPC. In the early days, when we talk about chemical processes, MPC is usually used to force a processor system to operate at a predefined set point or target. In the context, especially within energy systems, what we really want to optimize is not the tracking error or minimizing the tracking error, but rather we're trying to minimize some economically oriented objective, say the energy consumption or the energy cost. So that motivates this need for this more general framework. So when you hear economic MPC, really what we're talking about is optimizing the processor system economics directly, making decisions about that system to control it, and making those decisions on the basis of economics. So within the context of energy systems, what I'm trying to argue here is we really need this technology because in energy systems, often what we're faced is variable energy storage, time-varying electricity pricing, perhaps peak electric demand charges, as well as time-varying disturbances, all motivating this need to not only optimize the process economics, but look over this horizon, so that way we can make good decisions now. Okay, so again, didn't want to touch on the math, but this is my one math slide. I'm just going to take you through the key concepts, so you don't necessarily need to understand the math. And of the two parts of MPC, the first part is this concept of an optimal control problem. That optimal control problem, the first part is this objective function, which we specified on the basis of the economics. Again, we're doing this over a horizon into the future. The second part is this dynamic model. So we make forecasts about how the expected system or process will evolve over this horizon. subject to our decisions or control actions. And finally, we can incorporate constraints into this problem. So in the context of building HVAC systems, we have to respect occupant comfort considerations, so that shows up as a constraint in our problem. Okay, the second piece of model predictive control is this receding horizon implementation. And it actually has a really intuitive interpretation. So if we view MPC, how we typically or may typically make decisions about, say, how we want to plan out our week, right? We make a forecast over the entire week and kind of get an expectation on how the week will evolve so that we can make a decision about what we want to do today. Of course, over the course of that week, our expectation isn't perfect. Things come up, disturbance acts as on our quote system, and so we have to reforecast and make new decisions each day about what we want to do. And that's what this receding horizon implementation, it's this concept of constantly reforecasting, reoptimizing, making new decisions, giving current information. Okay, so this is sort of how it would look online. At a given time step, we make a forecast into the future. This allows us to make decisions, a sequence of decisions over time. We implement the first element of that sequence as a control action. At the next time step, we reforecast and reoptimize this sequence, and we implement the first element in that sequence. Okay, so as I said, I spent the last 8 years on MPC, but more specifically on the concept of economic MPC. Within my PhD, we looked at a number of theoretical works, which I won't have time to talk about today, but if you are interested, I have some citations here, and I encourage you to check out our papers on the topic. So after my PhD, I went on working in industry at Johnson Controls for 4 years, where we were mainly concerned with the area of energy systems, and more specifically, we were concerned with primarily HVAC systems. So within the context of this audience, many of you know these statistics, or these often cited statistics of buildings consume a ton of energy within the EU and US, and within that, HVAC systems account for a large percentage of energy consumption. And the HVAC energy consumptions often can be flexible. The consumption can be flexible. So now, I'm not the only one that has sort of connected the dots between buildings and MPC. In fact, if you Google those four terms, model predictive control buildings, you're going to come up with hundreds, if not thousands, of papers on the subject. And in fact, here's just a list of just the review papers alone. And all these studies, these are all research studies mostly, they report very key benefits of MPC with respect to other control techniques. More specifically, they report energy savings, operating cost savings, improved comfort, etc. So that's all well and great, but the question remains is, why doesn't every building in the US, in the world, have an MPC controlling it? And the answer, as I've thought about it over the course of 8 years, and sort of from my perspective, I think it boils down to really how MPC has evolved over time. Remember, it's evolved from the chemical process industries. So in the chemical process industries, if we consider the design, deployment, and operations of MPC systems, we consider the skill set of those folks doing those tasks. In each bubble, we're talking about very highly skilled individuals. So if we make a plot of expertise of MPC and the process systems operations, what we find is there's no decrease in knowledge between these three phases. On the other hand, if we're talking about building HVAC systems, and we talk about the design, deployment, operations side of things, in the design phase, we often have advanced control engineers that are doing the design. I was one of them when I worked at Johnson Controls as a PhD. But then when we talk about deployment, it depends on the business model of the particular business, but if we're talking about deploying through, say a company's branches, Then we were talking about potentially having a technical engineer or technician that's responsible for these deployments. They have knowledge of HVAC systems, but probably no knowledge of MPC. Then on the operations side, we're talking about a building operator in a commercial building type setting, or even in a residential situation, we're talking about a homeowner. And it's very unlikely that in the operations side of things, the expertise on HVAC systems and more specifically on MPC is going to decline and be very low, minimal, if not, if at best. So we get this decline. And so that's really what has, in my opinion, been the key problem that we have to solve with MPC to make it easy to deploy and easy to operate. So as part of my work really is motivated by those two slides, really trying to address this problem. One of the technical issues that we've been looking at over the course of the last several years is this concept of model identification. So within MPC, we have to define a model for the system to do our forecasting, and that ends up being a pretty substantial, developing that model and then training that model ends up being a pretty substantial source of costs in the deployment phase. So we have to develop robust techniques that can be easily implemented. The second concept that I've been working on for the last several years is considering this problem with implementers and users of these advanced control strategies are not typically control experts. Due to the time constraints, I won't get into this problem, but it is another area I work, and that is addressing this concept of the problems can be very large scale. If we're talking about a central energy facility or even a building with many thermal zones, the problem that we construct, the optimal control problem, tends to be very large scale. And so how do we solve that to meet real-time requirements for real-time control? Okay, so let's just talk about the first issue. Again, I'm only going to sort of touch on some of the key aspects of this work. So first, let's motivate the work. So if we're talking about a building, and this was, so in my PhD, I was very much in the chemical engineering realm, studied a lot of reactors, distillation columns. So I thought those were, the epitome of complexity. And then I got into industry and I started working on buildings, thought that are super simple, but then realized in a very short period of time that buildings are actually quite complex. They're really complex because of the fact that there's many different heat transfer, or there's lots of different sources of heat transfer within a building space. And specifically, there are unmeasured time-varying disturbances due to lighting, electrical equipment, occupancy, solar radiation, things that we can't measure but provide heat to a space. This lack of telemetry data makes the identification of this building model challenging. And so what we did in this work is we developed a modeling framework that can identify a low-order model, low order meaning this model has a few parameters that we can then embed in this predictive control framework and then use for real-time optimization. Okay, so just sort of the summary of the key end-to-end strategy here, not going into much technical detail, but what we developed was a parameter estimation procedure. Basically, what this procedure featured was a 2-day experiment level. So over that 2-day experiment, basically what we're doing is making small step changes to the temperature set point. We want to keep that experiment as short as possible, realizing that the building is occupied, so we want to respect occupant comfort. And what we found was over that 2-day window, that was enough data to then fit a model to our process. Again, this is a low-order model. But additionally, what we also did was fit what we call this Kelvin gain. And this Kelvin gain allows us to do this thing called disturbance estimation. Within the context of the building, disturbance estimation means all that sources of unmeasured heat gains to a building space. So really the key novelty was in this work was to do this identification of the estimator gain, but then go back and estimate from all the data that we've collected the disturbance over time. And from that estimate of the disturbance, then build a forecasting model that we call this disturbance forecaster. So for that, we used a machine learning LSTM, long short-term memory type model to do that model. Now, when it comes to the disturbance forecasting, of course, the disturbance is going to vary over time. So, you know, a weekday is going to look very different than a weekend for most buildings. And then over time, as, you know, say the solar loads change, that the loads will change as well on this space. So we want to make sure we need to collect more data than just the 2 days, but note that this data can be just regular operation data. It doesn't, we don't have to perform that those series of step changes to the building set point. Okay, so I'm going to skip this slide. I think actually the key point on this slide is really the time features we used in this model, and that is we're accounting for things like time of day, day of year, day of week. If I was actually implementing this in practice, we probably would add another one, and that is holiday and not holiday. You know, things that alter the type of operation of a building. Okay, so here's some example simulation results. The blue line is our predicted temperature over a course of a 1-day span. And then the black line is the actual temperature in this upper plot. In this lower plot is what we call the lumped temperature building mass. So it's a lumped building mass temperature, I mean. And again, we see pretty good agreement with between the actual and the input. So again, this is simulated, so we can actually extract out what the simulated building temperature would be, building mass temperature. The upper two plots, the first one is the sensible heat load on the space. So this is what the MPC would manipulate over time. So that's given over a trajectory. The other one is the outdoor air temperature, and that, you know, we have available forecasts that we can use to actually forecast that outdoor air temperature, dry bulb temperature over a day horizon. The last two would not be actually available for us for forecasting purposes. This would be the solar radiation and the internal loads. So you can see the profile, at least what that was in this simulated case. Okay, and then the other piece to this was the disturbance forecaster. So we just show that we get pretty good forecasting. The units are a little strange based on how the estimator works, but basically think of this as heat loads to the space, and we get a good agreement between the actual and the predicted. Okay, so the other key piece that I worked on, actually dating back to my days at Johnson Controls, was to really address this concept of implementers and users of advanced control strategies are not control experts. So basically what we did was we developed this optimal control-based solution for energy asset allocation. And our approach, again, we used economic model predictive control for all the same reasons that I've been describing in the talk. But really the key novelty here was we developed this graph-based EMPC system. So graph meaning nodes and edges in the mathematical sense and not like a plot or something, graph-based. And I'll give an example of that in a couple of slides. And so really this graph was the way that this graph worked, and the advantage of it is we were able to reduce a central plant, a description of a central plant, into a few number of objects, which we then could extract out the information from these objects and automatically create an economic MPC problem and solve that for online and real-time control. And these 4 objects included a supplier. So the way to think of that is it's a utility, it's an energy source that's supplied to the system. Can have demand response programs, it can have energy programs, etc. The second one was an asset. So think of that as something that converts energy. So let's say a chiller. It could also be used to store energy, so like a thermal energy storage tank. The third object is called a load, and that's just a demand. So in the central plant case, that could be a chilled water load. And the last one is a node, and it's just a point of balance. What goes into the node has to come out of the node, essentially. Okay, so then what we did was some other folks that are great at developing graphical user interfaces, better than me, as you could probably tell from my slide, developed this palette program where users could pull down different assets, connect them up into this graph to describe their particular central plant. So here's a sort of a depiction of that user interface with all the nodes of the graph connected. So in this case, we have some chillers, some hot water generators, some thermal storage tanks, and some utilities. So in the background, what we do is then we convert that into this graphical abstraction of the problem. So again, this is just the same problem, but now in that graphical abstraction. So each one of these blocks contains all the information that would be relevant to our economic MPC problem. So, you know, if, as an example, a chiller would include a chiller model. And that chiller model is going to contain all information that a user, say a plant manager, would know a priori. So what is the capacity of the chiller? What is the efficiency of the chiller? And then it creates the model automatically. If the efficiency is unknown, then we can learn it automatically and put that into to creating the chiller model. Okay, so I guess this is the second mathematical slide, but really the point here I try to drive home is that this system allows the user to interact with the MPC problem, basically allows them to specify the problem without any knowledge of the MPC, because what happens is that graph then gets converted into this beautiful looking formula. Okay, so I talked about two aspects that really tries to address this core problem, that is model construction, developing these robust model identification techniques. I also talked about this issue of deployment folks and operation folks don't usually have high expertise in the area of model predictive control. So that was my talk. I appreciate your time. I'd be happy to address any questions if we have any time.
Yeah, we have a few minutes. So if you have a question, please let us know and we will unmute you so you can ask your question to Matt. Thanks so much, Matt.
I'm wondering if you could talk a little bit about how this control style differs from conventional ways that HVAC systems are controlled.
Yeah, so today most HVAC systems are controlled usually with, or primarily with rules of thumbs. So I should specify the type of control we're really talking about with model predictive control is a supervisory control. So we're not really talking about, like, say, a VAV control that's doing regulatory control to control a VAV damper, as an example, right? We're talking about control above that that's making decisions system-wide to optimize. And within HVAC, primarily what's used is rules of thumb. And the reason why is because the industry as a whole tends to favor low-cost, easily to implement solutions, which rule-based is usually that, for the reasons that I sort of pointed out in this last slide, and that is the fact that the folks that are responsible or are living in those buildings tend not to have much knowledge of HVAC systems, so they need the systems to operate robustly and without minimal intervention.
Great. We've got another question. Dave Vernon, I'm going to unmute you here. You're on, Dave.
Great. Thank you, Professor Ellis. I enjoyed your very accessible entree to this topic. I wanted to ask you about the system discovery and how much of that is getting into like inverse modeling, and how deep do you need to go to make this valuable in the HVAC setting?
So you're talking about how deep does the deploy, or the folks that are deploying or operating the systems need to go, or are you talking about how deep do we need to go as design folks?
I was thinking about the system discovery that, and particularly interested in developing this automatic system discovery that would enable some of these systems to learn about the plants and the buildings on their own to specifically address the question and like how basically how much detail do they need to be able to get about the building in order to these automated learning systems in order to really be valuable compared to, you know, as an engineer, I imagine a whole bunch of detail that we would love to have, but how coarse can it be and still add value? If that's an
I think that's okay. Yeah. Thanks for clarifying the question. I think that's a really good question. I think that if we had, so say the central plant as an example, there still remains, I think the point here is there still remains some upfront costs of dropping that down. And if we could just do automatic system discovery and generate this sort of figure automatically, then it would prevent any need for any sort of intervention by the user. And then on top of that, what information would be needed. For this particular process or system, I should say, I think that there's a lot of that we can learn just from the data. And I think, so just knowing that we have a chiller asset, we can then use the data to learn some of these efficiency models. Obviously we know what a chiller, the usual measurements that a chiller would have, so therefore we can use that. And then when we talk about a building HVAC systems, we're talking about buildings with many zones. I think that there's a lot of things that we would like to specify, but can we still add value? I think in some of our work, we've shown that we actually can, even with minimal value. But I think overall, my expectation is, as we sort of think about the future of what these quote smart device, the information that will be contained on these devices that could then be used to say, hey, I'm connected to the system, so therefore account for me in the problem. I think that information is in general going to increase over time. So I think I'm optimistic in thinking that there'll be more availability of this, some of that data in the future as we talk about this discovery problem.
Great. And Devin had a question as to whether, she has another question. So I will unmute you, Devin. Oh, Devin may have stepped away. Devin, I think you're unmuted. We'll come back to you in a second. Claire had a question, and I'll ask her question as I unmute her. It was about whether MPCs have been used in microgrids or will be, or how do you anticipate that working?
Yeah, they're absolutely used in microgrids. Not exactly my area of expertise, so I can't tell you if there's how many industrial applications there are, so things that are actually controlling systems in real time today. But certainly there's been a pretty substantial amount of work done in the area, especially in the research community. Yes. And I think, again, anytime you need to really look over a horizon, I think this goes back to an earlier question, typical control strategies or most of the other control strategies where we just make a decision based on current information, that's not really well suited for when you actually need to look over a horizon. So in microgrids would be one of those where you're forecasting demand as an example over time.
Great. And we'll have one final question here, and that is, we'll have Robert ask that as we transition over to Fred. So I'll make Fred a presenter as we get this question here from Robert. So Robert, let me get you unmuted. Okay, Robert, you're on.
Thank you. Thank you. My question is, can you speak to how you are handling relearning of your parameters for your control system, especially regarding neural networks or machine learning? That can be a timely and computationally inefficient process, depending on whether you're doing it locally in embedded hardware or if you're utilizing Amazon servers for that. And additionally, can you speak to how often you are relearning based on local changes to conditions, daily, weekly, seasonally, so on.
Yeah, it's a good question. The relearning problem, there's a number of issues that we can look at there. So I'm just going to keep my response brief. In practice, so again, going back to my work at Johnson Controls, most of our stuff was implemented in the cloud, and primarily cost was a determining factor of doing this. So, if we're talking about buildings and we want to connect up buildings, it tends to be economically more viable to do that compute in the cloud, where we're actually connecting to site, sending the information. And so you have when you're talking about retraining, you do have the availability of the cloud. Now, in terms of frequency for relearning, that can vary from application to application. So I'll keep my response basically at the building space, those dynamics. And I unfortunately have not looked at that problem too much. We envision that it probably would be a once a year type of thing, once every season. So in the summer months, you perform this learning activity. Again, we're really talking about that 2-day window where we actually make active changes to the building. But beyond that, then you just collect regular operation data, and then you can make small adjustments to models based on that. Although, keep in mind that I haven't extensively looked at this topic. And that's just based on preliminary sort of results that I've seen in the field.
Great, thank you.
Hi, Matt. Thanks for your presentation. I have a question about the screen that maybe the results of the algorithm or the predictive control is displayed to operators, and how much time in the future do they see? Is it an instantaneous thing, or is it do they have a certain number of hours ahead to be able to kind of schedule equipment?
Good question. So in the screen that we show for the central plant optimization product, we actually forecast 7 days in advance. And the reason why we do 7 days is to account for have at least the upcoming weekend included in that forecast. And then in terms of scheduling, the equipment is scheduled automatically with the it's an automatic process done by the MPC. So the MPC is making these decisions and then implementing them directly, so the user doesn't actually have to interfere. Now, if the user has, say, equipment's going to be down for routine maintenance, they can schedule that in the system, and then it will automatically account for that in the control. On the building side, we forecast out 2 days, but probably it only makes sense to show a user a day of how the system will operate. And really what we're trying to do with buildings is leverage the building mass as energy storage. So usually what that means in the summer, we can do pre-cooling, and that's really what we'd want to show is the daily pre-cooling that we would do with the building. So if the user doesn't want to do pre-cooling on that day, they could potentially say, no, I don't want to do that, and adjust the profile.
Is this method used in any central plants anywhere? And if so, is there a publication about it?
Yeah, I think the flagship one that we did at Stanford University is pretty widely known, and I think you can find a lot of information on it. We have a number of patents on the approach too, so if you're looking at the technical ones, but in terms of white papers, there's probably the most amount of information in the public domain that can be found on Stanford Universities. We've done other ones, and in fact, since I've left, I'm sure they've have plenty of applications. But I just know that our first one, Stanford University, was the one that there's the most amount of public information available.
All right, thanks, Matt. And we have another question or two, but we'll save those for the end and get to those. I'm going to send everyone Matt's email address too, so if you wanted to follow up, you can reach him that way as well. And we'll get started with Fred. Welcome, Fred.
Hi, everyone. Thanks for sticking around. My name is Fred Meyers. I'm going to talk to you today about duct losses for variable speed residential HVAC systems. So, quick overview. Single speed equipment is probably what you have at home. It's got two modes, on or off. If you were to buy one today, it would be the cheaper option. Variable speed equipment, you can actually change the capacity of the compressor, the condenser unit. You can change the speed of the circulating fan and meet the load on the living space. And what this does is give you a nice, even temperature inside your house that is comfortable, and the single speed system can possibly fluctuate up and down since it's turning on and off at full speed. And the variable speed equipment also has much better efficiency. So this plot on the bottom right is showing the seasonal energy efficiency rating versus the size of the unit for single speed, dual speed, and variable speed systems. And the variable speed choice is going to be more efficient, but higher upfront costs. But there's more to efficiency than just the efficiency rating of the unit itself. Let's talk about delivery effectiveness real quick. So that is how much energy did you put in or take out of the airstream, and how much actually made it to the living space. So it's a ratio, 0 to 1, hopefully not 0. And most of the losses come from duct losses due to leaks and heat transfer, especially if you have ducts in the attic. So say you're cooling your house, the ducts are in a hot attic, and that heat transfer that occurs is going to make your system a little less efficient. How much does it affect it? Well, we have some experimental results from last year. There was Energy Bites that Curtis Harrington did. And so say you're running your equipment at a high speed. What's going to happen is air moves from the evaporator to the living spaces quickly. And this uses more power, but the effectiveness is good, the delivery effectiveness. Say you run your equipment at a lower speed. There's low demand for to cool your house or heat it, and there's low load, so your air is moving from the evaporator to the living spaces slowly, and you're using less power, but the effectiveness is poor, especially with the hot attic. So say your attic is 115 degrees, which is not unreasonable for California, and you're running your fancy variable speed equipment at a lower speed, you're actually not getting that good of delivery effectiveness. And this has a really big effect on the overall performance of the whole HVAC system of your house. But what does this mean for builders and code compliance? Well, in California, we have Title 24. And to meet Title 24 when building a new house, you have to meet a specified level of performance. You can build the house a lot of different ways. I'm oversimplifying here, of course, but in the end, it's just got to meet that performance criteria. And to predict whether or not you're meeting compliance, you can use CEC-approved modeling software that is free, called California Building Energy Code Compliance for Residences, CBEC-RES. And in the background of this program is another free open source modeling tool called the California Simulation Engine. And that's the heavy lifter in the background that's going through every time step throughout the year and figuring out the load on the house and how much energy you're using based on the construction you've defined. We've discovered, so now we've run into an issue. Let's talk about two scenarios. So scenario one, say a builder wants to spend less money on the HVAC system, so they design a high performance attic and use a lower cost single speed HVAC system. The modeling software will predict that compliance is met because you've moderated the temperatures of the attic space. So there's pretty good delivery effectiveness. So that's good. Scenario 2, a builder wants to save money on the attic construction. So instead they design an attic without roof deck insulation and use a more efficient variable speed HVAC system. So they're saving money on the roof and the attic, but they're spending money on the HVAC system to meet that performance criteria. And the modeling software predicts that the compliance is met. But in this case, the current modeling software does not accurately predict duct losses for the variable speed equipment. CSE actually calculates duct losses as if the equipment was single speed, even if you're designing with a variable speed piece of equipment. There's just no option for the user to define that, and it's not really the software's fault. You know, technology is evolving, so now we're running into a few issues, and how do we fix them? And how do we accurately model the duct system, and how far off is the current model? So to use a sort of a model based on a heat exchanger, we're going to talk about the duct system as having an efficiency. So it's got a overall heat transfer coefficient that includes the external airflow film resistance, the conduction through the insulation, and the internal airflow film resistance. It's going to depend on the duct surface area, the mass flow rate of the air, which is going to change depending on if you're running your variable speed equipment at a high speed or a low speed or whatever it's doing for you. And as a result, we can get the temperature at the end of the duct. And from that, we can calculate delivery effectiveness. To implement this, we're going to talk about the 2,100 square foot single story and 2,700 square foot two-story prototype buildings. These are just imaginary buildings defined by the California Energy Commission that are great tools for modeling, because if you just run the model as is on these prototypes, that is, you're meeting compliance perfectly. So it's a good baseline. Our general method here is to get the loads and current conditions from the modeling software, the current modeling software. So it's going to give us the load on the building, the weather, the attic temperature, stuff like that. From there, we can get the available capacity. So if it's really hot out and humid and perhaps the weather does affect the efficiency and the available capacity of the condenser unit and the indoor fan. So we can calculate that. And then we're going to guess, just straight up guess, a fractional capacity to run the equipment at and calculate the delivery efficiency from that, or delivery effectiveness. And that's an iterative method. So we guess and then we use Newton's method until we figure out at what capacity do we run this piece of equipment to meet the load. And after we figure that out, we can figure out the power used by the system. And we do this for every time step throughout a predefined year, a year that has a defined weather, and temperatures are available for each time step that we can get outdoor weather temperature, cloud cover, stuff like that. And the results are interesting. So comparing the two models, CSE is going to predict good delivery effectiveness no matter what speed or fraction of full capacity the equipment's running at. And this would predict that the house would meet code. This graph on the right, I'm missing a legend, apparently, sorry. Orange is going to be CSE, and blue is going to be our variable speed model. And the variable speed
Yeah, sure. So the end result was that the modeling software available from the state turns out to underestimate how much power you're actually using, and that's for all 16 California climate zones. And it's going to range the difference is going to range between close to 0% for the desert, like around Palm Springs. The numbers match up really well because you're actually running your cooling system almost 100% all the time, or at least a lot of the time. So the differences between the models are not significant. But for the other climate zones, we're talking about differences up to 30 or 40%, just for the HVAC system. That's not for the whole house, for all the electricity usage, but the HVAC system the differences are very significant. And this has gone to what's called the CASE initiative. So with collaborating with Frontier Energy, we've drafted a code change report to actually get Bill 24 to establish rules for zoning. And what zoning does, if you can have multiple zones in your house, you can turn off, say, the zones for your bedrooms and just cool your living room. And the velocity, the air velocity in your ducts will remain high, even at a lower fractional load. So you still get good delivery effectiveness. So zoning is a good thing. And we're planning on making that part of the code change, as well as suggestions for changing the modeling software itself to accurately calculate duct losses based on the actual mass flow rate of air in the ducts, not the full load flow rate, which it's doing now. And that's pretty much it. That's the summary off what I remember.
Great, thanks, Fred, and thanks for being patient. I'm sorry that happened. And one of the things about doing everything remotely is sometimes these things happen. So I appreciate your patience and getting back in. We do have a few minutes, so if anyone has questions, let us know, and Fred's on the line to answer them. I will also share Fred's email address and his video, this video, and Fred's complete presentation. We will make sure we include on the video link as well. Oh, he might be muted on his own end. Oh, he doesn't have audio. So I will ask his question. So he's wondering if it's overall it's better to use variable speed systems or not, just in the overall picture.
Depends on how your house is constructed. So the issue with the builders using this software and not getting the correct answer is that they'll not include roof deck insulation in your attic, for example. And so the attic will get really hot in the summer, really cold in the winter. And so variable speed equipment in that case would not be better than a single speed system. But if you can have both variable speed and a high performance attic, or if you have variable speed and zoning, then variable speed is much better.